In 1915, Albert Einstein wrote down 10 equations, just 10, and those 10 equations described gravity, space, time, the birth of the universe, the existence of black holes, and the ultimate fate of everything that has ever existed. But here is the disturbing part. When Einstein solved his own equations, the answers terrified him so much, he actually tried to hide them. He added a fake term to his own equations just to make the answer look less frightening. He was wrong to do that, and the universe eventually proved it. Today, we are going to solve those equations together, not with pages of calculus, but with honest, clear thinking, the way Feynman would. And by the end, you will understand exactly what Einstein saw that shook him to his core. G'day, and welcome back to Curious Physics AU, the channel where we take the universe's biggest secrets and explain them so clearly your nan could understand them over a cuppa. I am Abdullah, and today we are diving into what many physicists consider the most beautiful and profound piece of mathematics ever written, Einstein's field equations of general relativity. Now, before you panic, we are not doing a unimaths lecture here. We are doing something far more powerful. We are going to understand what these equations actually mean, what they are telling us about reality. Because here is the thing Feynman always said, mathematics is just a language. And like any language, once you understand what the words mean, the story becomes extraordinary. So let's read Einstein's story together. Let's go. Before we get to the equations, let us set the scene. You have probably heard of Newton's law of gravity. The apple falls, every mass attracts every other mass. Simple, elegant, worked brilliantly for over 200 years. But Newton's gravity had a dirty secret. Newton himself admitted it. He had no idea how gravity actually worked. He could calculate what gravity did, but not what it was. He wrote, and I love this, I feign no hypotheses, meaning I have no idea why this works. It just does. Fast forward to 1905. Einstein publishes his special theory of relativity, which we covered in our last video. Space and time are not fixed. They are flexible. They depend on how fast you are moving. But special relativity had a gap. It could not account for gravity. It only worked for objects moving at constant speeds. So Einstein spent the next 10 years working on the hardest problem of his life. How do you include gravity in a theory of space and time? In November 1915, he cracked it, general relativity. And the core idea is so simple and so radical. It rewired how every physicist on Earth thinks about reality. Gravity is not a force. Gravity is the curvature of space-time itself. Let me give you the analogy that every physics teacher in Australia uses, and then I am going to push it further than they usually do. Imagine space-time as a giant rubber sheet stretched out flat. Now place a bowling ball in the middle. The sheet curves downward around the ball. Now roll a marble across the sheet. Instead of going straight, it curves around the bowling ball. It follows the dip in the sheet, that curving path. That is what we call gravity. The Earth is not pulling the moon towards it with some invisible magic force. The Earth is curving the space-time around it, and the moon is simply following the straightest possible path through that curved space-time. In physics, we call that straightest possible path a geodesic. Now here is where I push the analogy further, and because the rubber sheet is actually misleading in one important way. The sheet only shows space being curved, but Einstein's equations tell us that time is also curved. This is crucial, and it is one of the most verified predictions in all of science. Time passes more slowly when you are deeper in a gravitational field. Here is a real Australian example. The GPS satellites orbiting Earth are in a weaker gravitational field than we are on the ground, so their clocks tick slightly faster by about 38 microseconds per day. That sounds tiny. But if engineers did not correct for this using Einstein's equations, your Google Maps would be off by about 10 kilometers every single day. General relativity is not abstract theory, it is running on your phone right now. All right, let us look at the equations themselves. Do not panic. We are not solving them. We are reading them. Einstein's field equations look like this. G-men plus L-G-men asks 8pg, C4, Tmin. Now, forget the symbols for a moment. Let me tell you what this equation is actually saying in plain English. The left side of the equation, G-men, describes the curvature of space-time. How bent is the fabric of the universe at any given point? The right side, 10, describes the matter and energy present at that point. How much stuff is here, how much energy, and the equal sign between them is the revolutionary part. It is saying matter and energy tell space-time how to curve, and curved space-time tells matter how to move. That is it. That is the whole theory, in one line. John Wheeler, one of the great American physicists, summarized it even more beautifully. He said, space-time tells matter how to move. Matter tells space-time how to curve. Now, that lambda term, L, that is the term Einstein added later, the one he regretted. We will get to that shortly, because that term, that single Greek letter, contains the most disturbing truth in the equations. But first, let us see what happens when you actually solve these equations. Einstein published his equations in November 1915. By December 1915, just 1 month later, a German physicist named Karl Schwarzschild solved them from the trenches of World War I. Seriously. And what did his solution reveal? If you compress enough mass into a small enough region of space, the curvature of space-time becomes infinite, a singularity, a point where the equations break down completely, where our understanding of physics simply stops working. We call this a black hole. Einstein was deeply uncomfortable with this result. He wrote papers arguing black holes could not really exist, that nature would somehow prevent them. He was wrong. We now know black holes are real. We have photographed one. In 2019, the Event Horizon Telescope captured the first ever image of a black hole in a galaxy called M87, 55 million light-years away. Here is the Australian connection. CSIRO's Australia Telescope Compact Array was part of the global network that made that image possible. Australian science, Australian technology, helping photograph a black hole. Now, a black hole is not like a giant vacuum cleaner sucking everything in. That is a common misconception. If our sun magically became a black hole right now, Earth would not get sucked in. We would just orbit it normally. The gravity at our distance would be identical. The difference is, if you got too close, past what we call the event horizon, the curvature of space-time becomes so extreme that not even light can escape. And without light escaping, we cannot see it, hence black. Now, here is the disturbing truth Einstein tried to hide. When you solve the field equations for the universe as a whole, not just around a single star, but for everything, the solution does not give you a static, stable, eternal universe. The mathematics says the universe must be either expanding or contracting. It cannot stand still. Einstein saw this result and hated it. The idea of a changing, dynamic universe felt wrong to him, philosophically uncomfortable. He believed, like most scientists of his era, that the universe was eternal and unchanging. So he did something rather embarrassing for the greatest physicist who ever lived. He cheated. He added that lambda term, the cosmological constant, to his equations. It was an artificial repulsive force designed to perfectly balance gravity and keep the universe static. He had no physical reason for it. He just needed the maths to stop telling him the universe was expanding. Then in 1929, astronomer Edwin Hubble made one of the greatest observations in the history of science. He discovered that galaxies are moving away from us, and the further away they are, the faster they are receding in every direction uniformly. The universe is expanding exactly as Einstein's original equations predicted. Einstein called the cosmological constant his greatest blunder. He removed it from his equations. He accepted the truth his own mathematics had been telling him for over a decade. And here is what makes that story so deeply human and so deeply scientific. Even the greatest mind of the 20th century had to fight against his own assumptions, had to be dragged by the evidence towards a truth he found disturbing. That is not a failure. That is how science works. But here is the twist that would have absolutely floored Einstein. In 1998, two independent teams of astronomers were studying distant supernovae, exploding stars, to measure how fast the universe was expanding. They expected to find the expansion slowing down. Gravity should be pulling everything back together gradually, right? Instead, they discovered the expansion of the universe is accelerating, not slowing down, speeding up. Every second, galaxies are flying apart from each other faster than the second before. Something is pushing space itself apart. something we cannot see, cannot detect directly, and cannot explain. We call it dark energy. And to account for it in Einstein's equations, physicists brought back the cosmological constant. That lambda term Einstein invented and then threw away in embarrassment. It turns out Einstein may have been right for the wrong reasons. Lambda is back, and this time it represents something real, something that makes up roughly 68% of all the energy in the universe. And we have absolutely no idea what it fundamentally is. Think about that. Nearly 70% of everything is something we cannot explain. Feynman would have loved this, not because it is frightening, but because it means the universe still has extraordinary secrets left to reveal. The equations are not finished with us yet. One last prediction from Einstein's field equations, one he himself doubted would ever be verified. When massive objects accelerate through space-time, they create ripples in the fabric of space-time itself, like dropping a stone in a still pond. We call these gravitational waves. Einstein predicted them in 1916. He also privately doubted we could ever detect them. They would be so incredibly tiny. On the 14th of September 2015, exactly 100 years later, the LIGO detector in the United States detected gravitational waves for the very first time, from two black holes colliding 1.3 billion light years away. The signal, when converted to sound, was a brief chirp, a fraction of a second, 1.3 billion years of two black holes spiraling together, and the universe sent us a chirp. General relativity confirmed. Every prediction, every solution, every disturbing truth the equations revealed, verified by observation. Einstein's field equations are arguably the most accurate and most profound description of physical reality ever written by a human being. So let us bring it all together, Feynman style. Einstein's field equations tell us that space and time are not a fixed stage on which the universe performs. They are dynamic, flexible, curved by matter and energy, and curving right back to tell matter how to move. Those equations predicted black holes, real. Predicted the expanding universe, real. Predicted gravitational waves, real. And revealed a mysterious dark energy, still one of the greatest unsolved puzzles in all of science. Einstein tried to hide the truth his own equations were telling him, and the universe patiently waited, then proved him wrong in the most spectacular fashion possible. And that, to me, is the most beautiful thing about physics. The universe does not care what we find comfortable. It just is what it is. And our job, as curious minds, is to keep asking, keep questioning, and keep following the maths wherever it leads, even when it leads somewhere disturbing. If you found this video useful, smash that subscribe button and join the Curious Physics AU family. New videos every week built for Australian students and anyone who reckons the universe is worth understanding. Leave a comment below. What disturbs you most about general relativity? The black holes, the expanding universe, dark energy? Tell me what blew your mind. Share this video with a mate who loves physics, or one who thinks they hate it. This might just change their mind, and I will catch you in the next one.